What if I told you that the very fabric of reality, the stage upon which the universe performs its grand dance, isn't smooth or solid at all, but more like a seething, bubbling foam, constantly churning at scales so small they defy imagination? This isn't science fiction. It's the wild frontier of quantum foam, a concept so strange it twists our understanding of space and time into knots. Picture this, down at the Planck scale, a realm a billion trillion times smaller than an atom. Spacetime itself isn't the serene, unbroken continuum we once thought. Instead, it's a frothy, turbulent ocean of fleeting particles and wormholes, popping in and out of existence in a frenzied dance. This is where the rules of physics as we know them break down, where gravity and quantum mechanics collide in a cosmic tug-of-war, and where the secrets of the universe might just be hiding. The idea of quantum foam isn't new. It was first proposed by the legendary physicist John Wheeler back in the 1950s, but it's only now, with cutting-edge theories and mind-bending experiments, that we're starting to peel back the layers of this cosmic mystery. Why does it matter? Because if quantum foam is real, it could rewrite the textbooks on everything from black holes to the birth of the cosmos. Imagine spacetime as a stretchy fabric, but instead of being smooth, it's riddled with tiny, unpredictable ripples and tears. Particles and energy flicker into existence, borrowing energy from the vacuum itself before vanishing again, like bubbles in a boiling pot. Some theories even suggest these fleeting fluctuations could spawn entire baby universes or shortcuts through spacetime wormholes hidden in plain sight. But here's the thing, quantum foam isn't just a puzzle for physicists in lab coats. It's a gateway to questions that strike at the heart of existence. What is reality, really? Are space and time fundamental, or just emergent properties of something deeper and more chaotic? And if the fabric of the universe is this unstable at its core, what does that mean for the future of everything we know? Over the course of this video, we'll dive into 30 mind-expanding theories about quantum foam, from the bizarre to the borderline unbelievable, each one pushing the boundaries of science and imagination. Some might sound like pure fantasy until you realize they're backed by math that's even stranger. So buckle up. We're about to take a journey into the quantum underworld, where the rules are made up, the laws of physics are optional, and the very nature of reality is up for grabs. Ready to step into the foam? John Wheeler's quantum foam hypothesis shattered the illusion of spacetime as a calm, unchanging backdrop. Instead, he proposed that at the smallest possible scales, down to the Planck length, a distance so tiny it's a decimal point followed by 34 zeros, reality is anything but smooth. Imagine taking a microscope to the fabric of the universe and seeing not a serene canvas but a storm. Tiny bubbles of energy, virtual particles, and even microscopic wormholes flicker in and out of existence like foam on a crashing wave. Wheeler's genius was recognizing that this chaos isn't random noise, it's a fundamental feature of spacetime itself. This wasn't just a poetic metaphor. Classical physics, from Newton to Einstein, treated space and time as a fixed stage where particles moved predictably. But Wheeler's quantum foam upended that idea, revealing a hidden turbulence where gravity, the force that shapes galaxies, collides with the bizarre rules of quantum mechanics. Picture throwing a rock into a pond. In classical physics, the ripples spread smoothly, but in quantum foam, the pond itself is made of boiling water, with tiny whirlpools appearing and vanishing faster than you can blink. That's the chaos Wheeler was describing, where spacetime isn't just warped by massive objects like stars, it's constantly twisting and churning on its own. What makes this theory so revolutionary is how it bridges two worlds. Quantum mechanics reigns at the subatomic level, where particles can be in two places at once. General relativity governs the cosmos, where black holes bend reality. But where these two titans meet, they clash violently, and quantum foam might be the missing link. Some physicists suspect these microscopic fluctuations could explain why gravity is so weak compared to other forces, or even how the universe sparked to life in the first place. If spacetime is a frothy sea at its core, then maybe the Big Bang wasn't a single explosion, but a bubble in an endless quantum foam. Wheeler's idea also forced us to rethink what nothing really means. A perfect vacuum, long thought to be empty, is actually seething with this quantum activity. Particles and antiparticles borrow energy from the void, exist for a fleeting instant, then vanish again like cosmic fireflies blinking in the dark. This vacuum energy might even hold the key to dark energy, the mysterious force accelerating the universe's expansion. Yet for all its brilliance, the quantum foam hypothesis leaves us with more questions than answers. How do we observe something so vanishingly small? Could these quantum bubbles create navigable wormholes, or are they just ephemeral glitches? And if space-time is this chaotic at its foundation, does that mean reality itself is fuzzy? Wheeler once said, "Reality is built on an immaterial foundation, a smoky dragon that vanishes when you try to pin it down." In quantum foam, we're staring straight into that smoke, and the deeper we look, the stranger it gets. If spacetime were a bridge, loop quantum gravity would be the engineer declaring it's not made of solid steel, but of trillions of tiny Lego blocks. This theory doesn't just tweak our understanding of quantum foam. It guts it entirely, proposing something radically different, a universe stitched together by an invisible web of spin networks. Forget smooth, continuous fabric here. Space itself is pixelated, built from microscopic geometric chunks vibrating in a cosmic symphony. Think of it like a cosmic tapestry where each thread isn't woven from spacetime, but from quantized loops of gravity itself, knotted together in relationships so precise they could rewrite physics. At the heart of loop quantum gravity is a simple but revolutionary idea. What if spacetime isn't fundamental at all? Instead of frothy quantum foam, imagine a vast network of intersections like an endless subway map where each station represents the tiniest possible unit of volume, and the tracks are gravitational fluxes linking them. These aren't metaphors, they're mathematical truths derived from smashing Einstein's general relativity with quantum mechanics. In this framework, a particle moving through space isn't gliding on a smooth surface, it's hopping from one discrete node to another, like a cosmic game of hopscotch played at the speed of light. Why does this matter? Because while Wheeler's quantum foam hints at turbulence, loop quantum gravity offers a way to quantify it. Each loop in the network carries a spin, a quantum property that defines how space itself curves and interacts. The beauty, unlike string theory's hidden extra dimensions, this framework keeps everything in our familiar three-dimensional world just pixelated. It's as if the universe has a built-in resolution limit, like a digital screen, where zooming in far enough reveals the pixels of reality itself. Some physicists believe these spin networks could solve one of science's biggest headaches, the singularity inside black holes. Instead of infinite density, there's a smallest possible unit of space, a cosmic stop sign for collapse. But the wildest implication, time might not exist at the most fundamental level. In spin networks, what we perceive as time could emerge from the changing relationships between these loops, like watching a movie emerge from still frames. This challenges Einstein's vision of time as a dimension, suggesting it's more like a collective illusion, a rhythm arising from quantum interactions. Picture a crowd doing the wave in a stadium. The wave isn't a thing, but a pattern emerging from individual actions. Similarly, time might just be the universe's most convincing group project. Critics argue that loop quantum gravity lacks experimental proof. After all, how do you detect spacetime pixels smaller than a quark? Yet supporters counter that its math avoids the infinities plaguing other theories, offering a cleaner marriage of quantum mechanics and gravity. And if it's correct, the implications are staggering. Wormholes could form naturally from tangled spin networks. the Big Bang might not have been a singularity, but a quantum bounce from a previous universe's collapse. Even dark energy could be a side effect of space's granular structure. The takeaway: loop quantum gravity doesn't just tweak the rules, it rewrites the game board. Whether it's the final answer or just another step toward a deeper truth, one thing's certain: the universe is far stranger and far more structured than we ever dreamed. And if spacetime is really a tapestry of spins, then every star, every planet, every you is just a pattern woven into its threads. String theory takes the chaos of quantum foam and turns it into something even more mind-bending: a cosmic hologram. Imagine the universe's deepest secrets aren't buried in its three-dimensional depths, but plastered like a movie on a two-dimensional surface at its edge. This isn't sci-fi, it's the holographic principle, a radical idea suggesting that every particle, every ripple in spacetime, even you, might just be projections of information encoded on a distant, flat boundary. And at the heart of this madness, quantum foam isn't random noise. It's the pixelated static of reality's projection screen. The key to this lies in the AD/CFT correspondence, a mathematical Rosetta Stone linking two seemingly unrelated worlds. On one side, you have anti-de Sitter space, a warped, higher-dimensional universe where gravity reigns. On the other, a conformal field theory, a flat, gravity-free sheet humming with quantum data. The revelation: these aren't separate realms, they're mirror images. Every event in the bulk of spacetime corresponds to a flutter on its boundary, like shadows dancing on a cave wall. The foam's frenzy, just pixels in a cosmic video game rendered in real time. Think of it like a credit card hologram. Tilt it, and a 3D image emerges from a flat surface. String theory proposes the entire universe works this way, with quantum foam as the shimmering artifact of data compression. Black holes amplify the weirdness. Their immense gravity suggests they swallow information irretrievably, yet holography insists it's all preserved on their event horizons, scrambled but intact. It's as if deleting a file on your computer didn't erase it, just moved it to the desktop wallpaper. But here's the twist: if holography is real, our tangible 3D world might be an illusion. The real universe could be a vibrating membrane trillions of times smaller than an atom, with quantum foam as the glitches in its rendering engine. Particles just tags in a cosmic database, forces, data streams between surface and bulk. Even time could be emergent, a byproduct of how information refreshes on the boundary. Critics argue this sounds like metaphysics, but the math is shockingly precise. Simulations of quark-gluon plasmas recreated in labs behave exactly as holographic models predict. And if spacetime is indeed a hologram, it solves a nagging paradox: why entropy scales with area, not volume, like bits on a hard drive, the foam's turbulence. Just the universe defragmenting its memory. So next time you stare at the night sky, consider this: those stars might not be distant flames, but pixels in a simulation so vast, even its glitches foam with meaning. Black holes, those cosmic vacuum cleaners that devour light itself, might be hiding a secret in their event horizons, and quantum foam could be the key. Picture the edge of a black hole not as a smooth, one-way gate, but as a seething storm of microscopic bubbles, each one a fleeting wrinkle in spacetime. According to some theories, these foam-like fluctuations aren't just background noise, they could be the fingerprints of Hawking radiation, the elusive glow that black holes emit as they slowly evaporate. It's as if the black hole's surface is a quantum foam factory, churning out particles and antiparticles in a frantic dance where some escape as radiation while others vanish forever into the abyss. But here's where it gets wilder. Some physicists argue that this foam isn't just a side effect, it could be the cause of one of the most heated debates in modern physics, the firewall paradox. Imagine falling toward a black hole. according to Einstein, you'd cross the event horizon without noticing anything unusual, at least until gravity stretched you into spaghetti. But quantum mechanics suggests the foam's violent fluctuations might turn that horizon into a blazing wall of energy, incinerating anything that dares to approach. Which is right? The answer might lie in understanding whether quantum foam is the glue holding spacetime together or the shredder tearing it apart. One provocative idea is that black holes don't just have quantum foam, they are quantum foam. Their interiors could be a turbulent sea of microscopic wormholes, each one a shortcut through spacetime's twisted geometry. Think of it like a cosmic sponge, with every pore a tunnel to another part of the universe or another time. This could explain why black holes store information so oddly. Instead of crushing matter into a singularity, maybe they scramble it into foam like microstates, preserving data like a hard drive encoded in spacetime's very fabric. Experiments might settle this sooner than you'd think. Gravitational wave detectors could someday catch echoes of quantum foam ripples in black hole collisions, tiny whispers of spacetime's granularity. And if we ever decode Hawking radiation's pattern, it might reveal the foam's structure like a cosmic barcode. Until then, black holes remain the ultimate quantum foam laboratories, where gravity and quantum mechanics battle for supremacy. And in that battle, the fate of reality itself might hang in the balance. Ever run your fingers over two nearly touching plates and felt an invisible force push them together? That's the Casimir effect in action, a phenomenon so strange it seems to pluck energy from pure nothingness. But here's the kicker: this eerie force isn't magic. It's quantum foam in disguise, with virtual particles, the universe's most elusive ghosts, playing the lead role. Picture a vacuum not as empty space, but as a writhing sea of temporary particle pairs popping into existence, borrowing energy from the void and vanishing again faster than light can cross an atom. Normally, these pairs cancel each other out, but squeeze them between two plates and something wild happens. Only certain wavelengths of particles fit in that narrow gap, leaving the outside teeming with more activity. The result, a subtle pressure that nudges the plates together, as if spacetime itself is sighing. This isn't just a lab curiosity. The Casimir effect is like lifting a corner of reality's curtain to glimpse the quantum foam beneath. Those virtual particles, they're the same frothy turbulence Wheeler imagined fleeting wrinkles in spacetime's fabric. Measure the force precisely enough, and you're practically weighing the foam's energy. Some theories suggest this effect could even reveal spacetime's granularity. Imagine pouring water through a sieve. If the holes are smaller than a certain size, the flow changes. Similarly, if quantum foam has a fundamental grain size, the Casimir force might tweak at scales we're just starting to probe, but the real bombshell. Virtual particles aren't just mathematical tricks. In 2017, researchers used ultra-fast lasers to catch glimpses of them winking in and out of the vacuum, like spotting ripples from fish you can't quite see. If these particles are the foam's bubbles, then every cubic centimeter of empty space is a maelstrom of creation and annihilation. That's the paradox of quantum foam. The emptier space seems, the more violently it churns. Now here's where it gets cosmic. The same energy driving the Casimir effect might be behind dark energy, the mysterious force accelerating the universe's expansion. If quantum foam's frenzy fills space with vacuum energy, could it be pushing galaxies apart? The math hints at a connection, though the numbers are notoriously tricky to align. Yet one thing's clear: the Casimir effect isn't just a quirky experiment. It's a window into the hidden turbulence scripting the universe's deepest rules, where nothing is never really nothing, and every vacuum hums with the static of existence itself. If quantum foam is the universe's hidden turbulence, dark energy might be its echo, an invisible force stretching spacetime apart at an ever-increasing rate. For decades, astronomers puzzled over why galaxies are fleeing each other faster than gravity alone can explain. The answer could lie in the vacuum itself, where quantum foam's ceaseless churning might be fueling the cosmos' runaway expansion. Picture this: every tiny bubble in the foam isn't just empty space but a pocket of repulsive energy, pushing outward like a trillion microscopic springs. At human scales, these forces cancel out, but across the vast emptiness between galaxies, they could add up to the mysterious pressure we call dark energy, a cosmic anti-gravity woven into the fabric of reality itself. The math hints at something extraordinary. When theorists calculate the energy density of quantum foam, adding up all those fleeting particle pairs and spacetime fluctuations, the numbers are catastrophically large. Like enough to unravel the universe in a nanosecond large. But here's the twist: in reality, dark energy's effect is subtle, a gentle nudge over billions of years. This mismatch, known as the cosmological constant problem, is arguably physics' greatest embarrassment. Some believe the solution lies in the foam's structure. Maybe most of that vacuum energy self-cancels, leaving behind only a faint residue, like the hum of a million voices whispering in perfect opposition, with just one stubborn note leaking through. That faint note, it could be the dark energy we measure. Alternative theories propose even wilder ideas. If spacetime is granular at the Planck scale, as loop quantum gravity suggests, then its discrete geometry might naturally generate repulsive forces as the universe expands, like stretching a mesh bag until its weave resists. Others speculate that quantum foam's microscopic wormholes act as pressure valves, siphoning energy from our universe into hidden dimensions. Then there's the holographic angle. If our 3D world is a projection from a 2D boundary, dark energy might be the cost of running the universe's software, with quantum foam as the processing glitches. The stakes couldn't be higher. If quantum foam and dark energy are linked, it could explain why the cosmos isn't just expanding, but doing so faster and faster. In one scenario, this acceleration might eventually tear atoms apart in a big rip. In another, the foam's energy could stabilize, leading to a frozen, eternal expansion. Almost unsettling of all quantum foam might be metastable, a shaky foundation that could someday collapse into a new vacuum state, rewriting the laws of physics instantaneously. Experiments are closing in. Precision measurements of distant supernova and galaxy clusters aim to detect subtle changes in dark energy strength over time, clues to whether it's truly a constant or something dynamic, tied to quantum foam's evolution. Meanwhile, tabletop experiments probing vacuum fluctuations might catch the foam's texture imprinted on microscopic forces. The dream, to spot the moment when a quantum bubble's push becomes a universe's fate. Until then, dark energy remains the ghost in the cosmic machine, and quantum foam the shadowy hand turning the gears. What if time itself could crystallize, not in the poetic sense, but as a real, physical structure that repeats its pattern not in space like a snowflake but in time? This is the bizarre world of time crystals, a theoretical phase of matter that pulses with perfect rhythm even in the lowest energy state, defying the usual laws of thermodynamics. Now imagine these strange structures emerging from the seething chaos of quantum foam. If spacetime is a turbulent ocean at the Planck scale, time crystals might be its most unexpected ripples, patterns that lock into a dance more precise than any atomic clock. The concept of time crystals was first proposed by Nobel laureate Frank Wilczek in 2012, inspired by the symmetry breaking that gives rise to ordinary crystals like diamonds. In a diamond, atoms arrange themselves in a repeating lattice, breaking the symmetry of empty space. Wilczek wondered, could something similar happen with time? Picture a system that, instead of freezing into a static configuration, settles into a loop of perpetual motion like a clock that ticks forever without needing to be wound. Experiments in 2017 proved such states exist, using chains of ions or spin-rich materials pulsed with lasers to create these time-bound structures. But here's where quantum foam enters the picture. If spacetime is fundamentally foamy, its flickering wormholes and virtual particles could provide the perfect breeding ground for time crystals. Think of it like shaking a snow globe. The foam's turbulence might nudge quantum systems into rhythmic patterns that persist even after the shaking stops. Some theorists suggest these crystals could act as tiny timekeepers embedded in the fabric of reality, their oscillations stable enough to resist decoherence, the quantum equivalent of noise. That stability is key. In a universe where quantum foam makes everything jittery, time crystals might be rare islands of predictability. Why does this matter? Because if time crystals can form in quantum foam, they could rewrite our understanding of time's arrow. Thermodynamics insists that disorder always increases, yet time crystals cyclically return to their starting state without energy input, a seeming paradox. One radical explanation is that they're tapping into the foam's vacuum energy, turning spacetime's chaos into a metronome. Others propose their evidence of time's granularity, hinting that what we perceive as a smooth flow is actually a cascade of discrete steps like frames in a cosmic film reel. The wildest possibility, time crystals might not just exist in quantum foam, they could shape it. If these structures interact with the foam's microscopic wormholes, they could stabilize fleeting spacetime tunnels, turning them into usable time loops. Far-fetched maybe, but in a universe where empty space boils with particles that shouldn't exist, and black holes erase information only to spray it back as holograms, far-fetched is just another Tuesday. For now, time crystals remain lab curiosities, but if future experiments find them lurking in the quantum foam's depths, we might uncover something profound. That time isn't a backdrop to the universe, but a material that can fracture, fold, and crystallize just like everything else. Wormholes, those fabled tunnels through space-time, aren't just the stuff of sci-fi. They might be hiding in plain sight, woven into the quantum foam's chaotic fabric. Imagine the froth of spacetime isn't just random noise, but a labyrinth of vanishingly small tunnels, each one a potential shortcut between distant points or even different times. These wouldn't be the grand, stable wormholes of interstellar travel, but fleeting, microscopic passages, ephemeral wrinkles in reality that blink in and out of existence faster than an atom can vibrate. Yet, according to some theories, these quantum wormholes could be the missing link between two of physics' most puzzling phenomena: spacetime's structure and the eerie connectedness of entangled particles. The idea hinges on a wild possibility that every time the quantum foam burbles with energy, it might pinch spacetime into tiny bridges. Picture a sheet of paper crinkling so intensely that opposite edges momentarily touch, creating a passage through the third dimension. In quantum foam, these pinches could form wormholes connecting regions that would otherwise be impossibly far apart. Some models suggest these micro-wormholes aren't just mathematical quirks. They could physically explain quantum entanglement, where particles instantaneously influence each other across vast distances. If two particles are linked by a wormhole too small to see, their spooky action at a distance might just be signals passing through a hidden spacetime tunnel. But here's the twist: these wormholes wouldn't be traversable in the conventional sense. They'd be unstable, collapsing before even a photon could slip through. Unless, and this is where it gets speculative, quantum foam's turbulence could be harnessed. Some theorists propose that under extreme conditions, like near a black hole's singularity or in the early universe's seething energy, these wormholes might stabilize long enough to function as cosmic shortcuts. Others argue that exotic matter with negative energy, something we've glimpsed in Casimir effect experiments, could prop them open artificially. The implications spiral outward. If quantum foam spawns wormholes, it could redefine our understanding of black holes, with their singularities potentially gateways to other universes. It might even offer a radical solution to the information paradox. What if lost data isn't destroyed but funneled through foam-borne tunnels to somewhere else? And if entanglement relies on microscopic wormholes, then the very fabric of reality might be far more interconnected than we ever imagined, a vast network of hidden threads stitching the cosmos together. Experiments are already probing this frontier. Quantum simulators use ultra-cold atoms to mimic wormhole dynamics, while gravitational wave detectors hunt for faint echoes of spacetime's foamy structure. The dream, to catch a fleeting wormhole in the act, proving that the universe's wildest shortcuts are lurking in the quantum foam's depths. Until then, one thing's clear. If spacetime is a frothy sea, its bubbles might not just be chaos, they could be doorways. Dark matter, the universe's most elusive ghost, might not be made of exotic particles at all, but of quantum foam itself. This radical theory suggests the missing mass holding galaxies together isn't some undiscovered substance, but the very texture of spacetime, warping gravity at cosmic scales. Imagine the quantum foam's turbulent bubbles aren't just microscopic noise, but tiny knots of gravitational energy dense enough to bend light and steer stars. These wouldn't be particles in the traditional sense, but fluctuations so persistent they collectively act like an invisible scaffold, propping up the cosmos. The math behind this is as elegant as it is unorthodox. If spacetime's foam-like structure varies in density, some regions frothing more intensely than others, those denser patches could curve space exactly like concentrated mass. Picture a rubber sheet dimpled by countless invisible pins. From afar, it sags as if weighed down by a single heavy object. Similarly, quantum foam's uneven churn might create gravitational shadows we misinterpret as dark matter halos enveloping galaxies. No new particles needed, just the wrinkles in reality's fabric finally accounting for their own weight. Critics pounce on a glaring hole. How could quantum foam, typically thought to operate at the Planck scale, affect something as vast as galactic rotation? The answer might lie in cascading effects. Just as a single butterfly's flap can amplify into a hurricane, quantum foam's microscopic gravity gradients could scale up through chaotic dynamics, imprinting their influence on interstellar distances. Some models even suggest dark matter's famous cuspy halo problem, where simulated halos are denser than observed, could resolve if foam-induced gravity smears out at larger scales, like blending a pointillist painting into softer gradients. The smoking gun, look to the bullet cluster where colliding galaxies seemingly left dark matter trailing behind visible matter like a gravitational shadow. If quantum foam underlies this phenomenon, its structure would need to interact weakly with normal matter while still warping spacetime dramatically, a tall order. Yet intriguingly, certain modified gravity theories tied to foam like spacetime predict exactly this behavior, with no need for WIMP or actions. Even dark matter's reluctance to clump too densely might find explanation. Quantum foam's energy could repel itself at small scales, preventing the overconcentration that plagues particle-based models. Experiments hunting foam's gravitational fingerprints are already underway. Ultra-precise atomic interferometers monitor free-falling particles for anomalies that might betray spacetime's granularity. Others analyze neutron star vibrations for patterns matching foam-induced gravity waves. If these efforts catch quantum foam pressing down on cosmic scales, we might not just solve dark matter's riddle, we'd prove that the universe's biggest mysteries were woven into its smallest stitches all along. Black holes have long been considered the universe's ultimate dead ends, places where matter crushes into an infinitely dense singularity and vanishes from reality. But what if that's not the end of the story? Enter Carlo Rovelli's Planck star hypothesis, a daring twist on cosmic collapse that turns black holes into cosmic trampolines. Imagine a dying star so massive it implodes under its own gravity, but instead of vanishing into a singularity, its core rebounds like a spring compressed to the absolute limit. This isn't science fiction, it's a radical rethink of quantum foam's role at the edge of oblivion. At the heart of this idea lies a simple but profound shift. Quantum foam might be spacetime's ultimate shock absorber. When a collapsing star reaches Planck-scale densities packing more mass than the Sun into a space a trillion times smaller than an atom, the foam's chaotic churning could halt the descent. Picture squeezing a sponge so tightly that its structure pushes back, resisting further collapse. In Revell's model, this quantum resistance creates a Planck star, a fleeting, ultra-dense object where gravity and quantum forces reach a temporary truce. For a split second, the star's core becomes a knot of spacetime foam so intense it glows with the heat of the Big Bang itself before rebounding outward. The implications shatter textbook physics. First, no singularity. Instead of infinite density, you get a quantum bounce, a moment where the star's collapse reverses, spewing energy back into the universe. Second, time dilation near black holes takes on a new meaning. To an outside observer, the rebound would appear frozen, stretched across billions of years due to relativistic effects. But from the star's perspective, the bounce happens almost instantly, like a firework flaring and fading in slow motion from afar. This could explain why we've never detected a true singularity. They might not exist at all. But the wildest consequence, Planck stars could be cosmic time capsules. Some theorists speculate that the rebound wouldn't just release energy, it might encode information about the star's pre-collapse state into Hawking radiation, solving the infamous black hole information paradox. It's as if the quantum foam acts as a cosmic hard drive, briefly preserving data in its frothy structure before rewriting it into the universe's background hum. Critics argue that detecting Planck stars is nearly impossible. Their rebounds would be hidden behind black hole event horizons, and their lifetimes are shorter than a photon's blink. Yet supporters counter that subtle fingerprints might linger. Gravitational wave observatories could someday catch echoes of these bounces in the ripples from merging black holes, like hearing the faint ring of a bell in a distant storm. Others suggest that high-energy cosmic rays might carry traces of Planck star emissions, scrambled but decipherable. Revell's hypothesis does more than rescue stars from singularities. It paints quantum foam as the universe's ultimate safety net, a frenzied but finite boundary where spacetime refuses to tear. Whether or not Planck stars exist, their possibility forces us to confront a thrilling question. What if black holes aren't endings but cosmic metamorphoses with quantum foam as the catalyst? After all, in a universe built on uncertainty, even the darkest pits might have hidden springs. If quantum foam is the universe's simmering foundation, could it also be the birthing ground for entirely new universes? This is the spine-tingling premise behind bubble multiverse theory, where the same frothy turbulence that twists spacetime at the smallest scales might also spawn cosmic offspring, each with its own unique physics. Picture the quantum foam not just as a seething sea, but as a cosmic incubator. Every flickering bubble in this foam has the potential, under the right conditions, to inflate into a full-fledged universe, bubbling away from its parent like a droplet breaking free from a rolling boil. The mechanism hinges on vacuum fluctuations, those fleeting particle pairs that borrow energy from nothingness. In most cases, these fluctuations vanish almost instantly. But if a bubble in the quantum foam pinches off with enough energy, it could undergo what's called false vacuum decay, a runaway expansion that warps spacetime so severely it effectively creates a new pocket of reality. Think of it like a pot of water heated past boiling. Most bubbles pop harmlessly, but occasionally one grows so large it carries steam far beyond the pot's edge. In this scenario, the steam is an entire universe, complete with its own fundamental constants, perhaps even its own number of dimensions. String theory adds another layer of strangeness. If our universe is a 3D projection from a higher dimensional boundary, as holographic principles suggest, then these baby universes might not just be separate, they could be stacked like pages in an infinite book. Quantum foam's wormholes might thread them together, creating a network of hidden connections. Some models even propose that the laws of physics in each universe are determined randomly during this bubbling process, like a cosmic dice roll. One universe gets stronger gravity, another has no weak nuclear force. Ours, with its Goldilocks perfect constants, might just be a lucky accident in an endless multiverse casino. Evidence for this wild idea is speculative but tantalizing. Certain anomalies in the cosmic microwave background, the afterglow of the Big Bang, show unusual cold spots that some physicists argue could be bruises from collisions with other bubble universes. Others suggest that if our universe was born this way, its expansion might carry subtle imprints of its quantum foam origins, like stretch marks from a violent birth. And if black holes truly are Planck star factories, their rebounds might not just reignite singularities, they could spark entirely new spacetime bubbles, birthing universes within universes in an endless fractal chain. The philosophical implications are staggering. If every quantum fluctuation has the potential to become a cosmos, then reality isn't just one universe evolving. It's a frothing, branching multiverse where every possible physical law plays out somewhere. The foam beneath our feet might not just be the fabric of our reality, but the soil for countless others, each blooming unseen in dimensions we'll never touch. And if that's true, the ultimate question isn't, why is our universe here? It's, which bubble are we? Quantum foam might be the universe's ultimate buzzkill, at least when it comes to the mind-bending weirdness of quantum superposition. You've probably heard of Schrödinger's cat, that unfortunate feline stuck in a box being both dead and alive until someone peeks inside. That's the magic of quantum mechanics at tiny scales. Particles can exist in multiple states at once, like spinning coins that haven't landed. But here's the puzzle. Why don't we see elephants or planets in superpositions? Why does the quantum weirdness vanish as things get bigger? The answer might be hiding in the frothy chaos of quantum foam, where spacetime's turbulence could be constantly nudging particles to pick a side. This process is called quantum decoherence, and it's like trying to balance a pencil on its tip in a hurricane. At microscopic scales, particles can maintain their delicate superpositions because they're isolated enough to avoid disruptive bumps. But quantum foam suggests spacetime itself isn't a tranquil stage. It's more like a mosh pit with virtual particles popping in and out, microscopic wormholes twisting geometry, and energy fluctuations kicking systems out of their quantum trance. Every time a particle interacts with this seething background, it's like getting jostled by an invisible crowd, forcing it to collapse into a single classical state. The foam, in other words, might be the reason reality looks so solid at our scale. Some models take this further. If quantum foam's fluctuations are strong enough, they could act like a cosmic measurement device, constantly observing quantum systems without needing a conscious observer. This would explain why superposition fades so quickly for larger objects. They're simply too big to dodge the foam's relentless noise. Imagine trying to nap in a room where someone's randomly flicking the lights on and off. Eventually, you'd give up and just stay awake. That's what quantum foam could be doing to particles, ruining their chance to stay in multiple states by bombarding them with spacetime's version of a strobe light. But there's a twist. Not all foam is created equal. In some theories, the intensity of decoherence depends on how loud the quantum foam is in a given region. Near a black hole's event horizon, where spacetime is stretched to its limits, decoherence might happen almost instantly, shredding quantum states like paper in a storm. In the quiet voids between galaxies, though, superpositions could linger longer, like whispers in an empty cathedral. This could even affect quantum computers' machines that rely on maintaining superpositions to perform calculations. If quantum foam's turbulence varies across space, placing a quantum computer in the right spot might shield it from decoherence, like tuning a radio away from static. The wildest implication, decoherence might not be a bug but a feature. If quantum foam forces particles to choose states, It could be the mechanism that stitches the fuzzy quantum world into the crisp reality we experience. Without it, the universe might be an endless haze of overlapping possibilities, with no definite outcomes, no stars, no planets, no you. So next time you marvel at the solidity of your coffee cup, thank the quantum foam's chaos for making it behave. Because in a quieter universe, that cup might still be hovering between the table and the floor. Einstein would be stunned to learn that his two greatest ideas, general relativity and quantum mechanics, might be two sides of the same cosmic coin, linked through the quantum foam's hidden tunnels. This is the heart of the ER=EPR conjecture, a revolutionary idea suggesting that every pair of entangled particles isn't just mysteriously connected, they're literally threaded together by microscopic wormholes buried in spacetime's seething foam. Picture two electrons born from the same quantum event, instantaneously influencing each other across light years, as if flipping a coin in Tokyo makes one in New York land heads up. Spooky action at a distance, right, but what if their link isn't magic, just physics we're only beginning to grasp? The conjecture's name is a mashup of two landmark papers. Nods to Einstein and Rosen's 1935 work on wormholes, Einstein-Rosen bridges, while EPR references Einstein, Podolsky, and Rosen's later paper highlighting quantum entanglement's paradox. For decades, these concepts lived in separate worlds, wormholes as relativistic curiosities, entanglement as a quantum quirk. But in 2013, physicists Juan Maldacena and Leonard Susskind proposed a bombshell: what if they're the same phenomenon, just viewed through different lenses? In this framework, every entangled particle pair shares a Planck-scale wormhole, a twist in the quantum foam so tiny it's imperceptible, but profound enough to tether the particles across any distance. Here's where it gets wild. Normally, wormholes' hypothetical shortcuts through spacetime require exotic matter to stay open, defying physics' known rules. But quantum foam's ephemeral wormholes wouldn't need stabilizers. They'd be fleeting yet fundamental, woven into spacetime's fabric like stitches in a quilt. When particles entangle, their wormhole forms automatically, a cosmic umbilical cord threading through higher dimensions. This could explain entanglement's instantaneity without violating relativity's speed limit. The particles aren't communicating, they're already connected by a hidden spacetime tunnel. The implications ripple across physics. Black holes, long thought to destroy information, might encode it in Hawking radiation via entanglement-powered wormholes. The holographic principle gains new texture. If our three-dimensional world is a projection, entangled particles could be pixels linked by underlying data threads. Even dark energy might emerge from the foam's wormhole network, its repulsive force the collective sigh of countless microscopic tunnels straining spacetime's weave. Critics argue the conjecture is still more math than observation, yet experiments are inching toward validation. Quantum simulators recreate wormhole-like dynamics using entangled qubits, while gravitational wave detectors hunt for echoes of spacetime's foamy structure. If ER=EPR holds, it would mean the universe isn't just stranger than we imagined, it's more intimately connected, with every quantum handshake leaving a microscopic wormhole in its wake. And that realization might finally bridge Einstein's two warring worlds into a single, breathtaking theory of everything. What if our entire universe was just a bubble in an endless cosmic froth? A single fluctuation in an infinite sea of quantum foam. This theory takes the Big Bang story and flips it on its head, suggesting that the cataclysmic birth of everything we know might have been something far quieter, a tiny ripple in spacetime's turbulent depths that swelled into reality. Picture the quantum foam not just as the universe's fabric, but as its nursery. In this view, the Big Bang wasn't a unique explosion. It was a perfectly ordinary event in a much grander multiverse, where new universes constantly bubble into existence like foam cresting on an ocean wave. The math behind this is as elegant as it is humbling. Quantum foam's fluctuations aren't just random noise, they follow the rules of uncertainty, meaning even the vacuum of space crackles with potential energy. Most of these fluctuations vanish instantly, but occasionally, through sheer statistical chance, one grows large enough to escape the foam's grip. When that happens, the bubble can undergo inflationary expansion, stretching from Planck-scale insignificance to cosmic vastness in a fraction of a second. Our universe, in this scenario, might simply be the lucky one that got away, its initial conditions set by the quantum dice roll that birthed it. Supporters of this idea point to the eerie fine-tuning of our cosmos. Why do the fundamental constants, the strength of gravity, the mass of an electron, seem perfectly calibrated for life? If countless universes are constantly bubbling up in the foam, each with random physical laws, it's no wonder we find ourselves in one where the numbers lined up just right. It's the ultimate application of the anthropic principle. We're here because this particular bubble allowed it, while trillions of others fizzled out or collapsed into nothingness. But here's where it gets surreal. If the Big Bang was a quantum foam fluctuation, what's outside our bubble? Some theories suggest a meta-universe where spacetime has radically different properties, perhaps with more dimensions or alternate physics. Our entire cosmos could be drifting in this primordial foam, occasionally brushing against other bubble universes. There's even speculative math showing how these collisions might leave scars in our cosmic microwave background, faint circular patterns where another universe once grazed ours. And if that's true, the night sky isn't just a window into our past, it's a murky lens into the foam's infinite depths. The most radical implication: time might not have started with the Big Bang. If our universe is a bubble in a larger foam, the meta-universe could be eternal, with no beginning or end, just an endless simmer of creation and destruction. The Big Bang becomes less of a bang and more of a phase transition, like water freezing into ice. This could resolve one of cosmology's great puzzles: what came before? The answer: more foam, eternally recycling itself. Of course, not everyone's convinced. Critics argue that without observable evidence of other bubbles, this remains philosophical speculation. But upcoming telescopes designed to study the cosmic microwave background in unprecedented detail might spot those telltale collision marks. Others suggest that gravitational wave astronomy could detect echoes of pre-Big Bang events, like listening for the faintest whispers of a parent universe. Until then, the quantum foam's deepest secret, whether it's the cradle of all reality or just one more beautiful hypothesis, remains tantalizingly out of reach. One thing's certain: if this theory holds, humanity's place in the cosmos is even humbler than we imagined. We're not just stardust, we're the fleeting afterglow of a quantum hiccup, riding a bubble in an ocean where universes are born and die like sea foam on the tide. And somewhere in that infinite froth, another bubble might be brewing with laws so alien they'd make our physics look like child's play. Fractal geometry is nature's favorite blueprint. The branching of trees, the jagged edges of coastlines, even the looping rivers carved into continents. But what if the universe's deepest architecture follows the same pattern? Enter fractal quantum foam, a mind-bending theory that suggests spacetime's turbulence isn't random chaos. It's an intricate, repeating tapestry where miniature versions of cosmic structures hide in the foam's tiniest crevices. Picture zooming into a fractal like the Mandelbrot set, where every level of magnification reveals the same swirling motifs. Now imagine spacetime behaving the same way. Galaxy clusters mirrored in Planck-scale bubbles, cosmic voids echoing inside quantum fluctuations. This isn't just artistic whimsy, it's a radical lens on reality's hidden order. The math behind this is staggering. Traditional quantum foam models treat spacetime's fluctuations as disordered, like static on a broken TV. But fractal geometry introduces scale invariance, a property where patterns repeat whether you're observing light years or trillionths of a millimeter. Apply this to quantum foam and suddenly, the universe's large-scale structures, filaments of galaxies, vast empty voids, might be shadows of the same geometries vibrating at the Planck scale. Think of it as cosmic déjà vu. The same shapes sculpted by gravity on galactic scales could emerge from spacetime's froth at the smallest levels, like a Russian nesting doll where every layer whispers the same secret. Why would foam behave this way? One clue lies in how gravity and quantum mechanics intertwine. Just as turbulent fluids form whirlpools within whirlpools, the interplay of these forces might generate self-similar spacetime wrinkles. Some string theory variants even suggest that fractal foam could arise from higher dimensional branes folding in on themselves, imprinting their geometry across scales. The wildest implication: if the foam is truly fractal, then black holes, those gravitational maelstroms, might resemble, in their event horizons, quantum turbulence, the very structure of the cosmos they devour. A universe in a black hole's fringe isn't just poetic, it could be woven into spacetime's DNA. Evidence for this is tantalizingly indirect. Astronomers mapping the cosmic web, the sprawling network of galaxies, notice uncanny resemblances to neural networks or even microscopic crystal formations. Simulations of quantum gravity often produce fractal-like spacetime lattices without researchers programming them in. And if holography is correct, our 3D universe's information being projected from a 2D boundary would naturally encode scale-invariant patterns like a fingerprint smudged across dimensions. But the real test may come from black hole physics. Fractal foam predicts that a black hole's entropy, a measure of its hidden information, should scale not with its volume, but with its surface area's intricate, crinkled texture. Future gravitational wave detectors might spot echoes in merger events that betray this frothy, layered structure. Meanwhile, tabletop experiments with ultra-cold atoms could simulate fractal spacetime's behavior, offering glimpses into how patterns propagate from the quantum to the cosmic. What makes this theory so mesmerizing isn't just its elegance, it's the audacious possibility that the universe doesn't have a smallest or largest scale. Instead, it's a boundless hall of mirrors where every level reflects the others in an infinite dance. From the foam beneath your fingertips to the voids between galaxies, reality might be humming the same geometric tune, a symphony of scales, with spacetime itself as the conductor. And if that's true, then the cosmos isn't just stranger than we imagined. It's more beautifully patterned than we ever dared to dream. Neutrinos are the universe's ultimate shape-shifters, ghostly particles that can switch identities mid-flight, oscillating between three flavors: electron, muon, and tau. For decades, this bizarre behavior puzzled physicists. But what if the answer lies not in the neutrinos themselves, but in the turbulent quantum foam they're passing through? Imagine these particles as tiny ships navigating a stormy spacetime sea, where the foam's churning bubbles and microscopic wormholes subtly tweak their properties, nudging them to transform from one flavor to another. If true, neutrino oscillations could be the cosmic breadcrumbs leading us straight to quantum foam's doorstep. The math behind this is as elegant as it is wild. According to quantum mechanics, each neutrino flavor isn't a distinct particle but a probabilistic mix of three mass states. As neutrinos travel, these states evolve at different rates due to their slight mass differences, causing the flavor to oscillate. But here's the twist: if spacetime is frothy at the Planck scale, its fluctuations could interact with these mass states like invisible currents altering a swimmer's path. Picture rolling dice on a wobbly table. The uneven surface doesn't change the dice, but it affects how they land. Similarly, quantum foam's turbulence might introduce tiny, stochastic shifts in neutrino phase relationships, amplifying or dampening oscillations in ways that pure vacuum physics can't explain. Experiments are already hinting at anomalies. Neutrinos fired through Earth, like those in the famous opera, and T2K experiments sometimes oscillate more or less than predicted, especially over long distances. While many chalk this up to measurement errors or incomplete models, A fringe but growing group of theorists argues these discrepancies could reflect spacetime's granularity. If quantum foam's structure varies along the neutrino's path, denser near massive objects like Earth's core, frothier in the void, it might create oscillation patterns that mirror spacetime's hidden texture. The implications are staggering. If neutrino oscillations betray quantum foam, we'd have our first indirect observational tool to probe Planck-scale physics. Forget building a microscope small enough to see spacetime's bubbles. We could use neutrinos as natural particle probes. Their flavor changes a cosmic Morse code spelling out the foam's structure. Future experiments like Dune and Hyper-Kamiok, and with their ultra-precise detectors buried miles underground, might catch these subtle fingerprints. Even more tantalizing, if foam's influence on neutrinos depends on energy, high-energy astrophysical neutrinos like those from distant supernova could reveal how spacetime turbulence scales across the universe. Critics counter that current anomalies are too faint to claim foam's involvement, and conventional physics might yet explain them. But supporters fire back. If quantum foam is real, its effects should be subtle. After all, we're not looking for a sledgehammer smashing neutrinos, but a whisper of turbulence ruffling their quantum phases. And if the whisper matches predictions, we'll have cracked open a window to the universe's smallest scales, not with a telescope, but with the most elusive particles in existence. So next time a neutrino changes flavor, remember, it might not just be dancing to its own quantum tune, but surfing the frothy waves of spacetime itself. Light has always been the universe's ultimate speedster, racing through the vacuum at an unwavering 299,792,458 meters per second. But what if that sacred number isn't as constant as we thought? Enter one of quantum foam's most startling possibilities, that spacetime's turbulent foundations might subtly tweak light's velocity, making it stumble ever so slightly as it navigates the foam's microscopic minefield. This isn't just a tweak to Einstein's relativity, it's a cosmic speed trap hidden in the fabric of reality itself. The theory hinges on spacetime's granularity. If the universe is pixelated at the Planck scale, then light, usually depicted as gliding smoothly through empty space, might actually be hopping unevenly across spacetime's tiniest bumps and dips. Picture a marathon runner on a track littered with pebbles. Even if they maintain an average pace, their stride falters with every tiny obstruction. Similarly, photons could experience fleeting delays or accelerations as they interact with quantum foam's frothy structure, especially at extremely high energies where their wavelengths approach the foam's grain size. The smoking gun for this effect might come from gamma-ray bursts, cosmic explosions so violent they launch photons with energies trillions of times higher than visible light. If quantum foam alters light's speed based on energy, these ultra-high-energy gamma rays should arrive at Earth slightly later than their lower-energy counterparts after crossing billions of light-years. And in 2009, NASA's Fermi Gamma Ray Space Telescope caught something intriguing. Gamma rays from a burst 7 billion light-years away showed no such delay. At first glance, this seemed to debunk the idea until theorists realized the energy differences Fermi tested might still be too low to reveal foam's subtle grip. But here's the twist. Some models suggest quantum foam's effect on light isn't uniform. Instead of a simple slowdown, foam could scramble light's phase coherence, the property that keeps laser beams razor-sharp over distance. In this scenario, the speed variation wouldn't show up as a clean delay, but as a blurring of starlight over vast distances, like a flashlight beam dimming as its photons scatter. Experiments like Veritas and the upcoming Cherenkov telescope array are hunting for this telltale fuzziness in distant quasars, where light has traversed eons of frothy spacetime. Skeptics argue these effects are too minuscule to detect, buried under cosmic noise. Yet proponents counter that quantum foam's fingerprints might be hiding in plain sight, encoded in the polarization of ancient light from the cosmic microwave background. If spacetime's granularity twists light's orientation during its 13.8 billion-year journey, those twists could linger like fossilized ripples, waiting for next-generation telescopes to decode them. The implications go beyond academic curiosity. If light's speed fluctuates in quantum foam, it could rewrite our understanding of causality, the bedrock of physics. Events separated by vast distances might not have a clear before and after if their light signals get tangled in spacetime's turbulence. Even black hole singularities, those supposed endpoints of physics, might dissolve into foamy uncertainty before they can break reality's rules. For now, the quest continues. Every photon racing toward Earth carries not just starlight, but whispers of the quantum sea it crossed, and with each new observation, we're learning to listen. Black holes aren't just cosmic vacuum cleaners, they're also the universe's most notorious data shredders, or so we once thought. According to classical physics, anything that crosses a black hole's event horizon is lost forever, crushed into oblivion at the singularity. But quantum mechanics insists that information can't just vanish, it has to go somewhere. This contradiction, known as the black hole information paradox, has kept physicists awake for decades. Enter quantum foam, the universe's most chaotic librarian. What if the secret to preserving information isn't in the black hole's depths, but in the frothy turbulence right at its edge? Picture an event horizon not as a smooth boundary, but as a seething storm of microscopic bubbles and wrinkles in spacetime. In this model, as matter approaches a black hole, it doesn't plunge straight in, it gets scrambled into the quantum foam's chaotic structure, like a message shredded into confetti but with every piece meticulously tagged. Instead of being destroyed, the information gets imprinted onto the foam's flickering patterns, encoded in the way spacetime twists and churns at the Planck scale. Think of it like throwing a book into a hurricane. The pages might scatter, but the words are still floating in the storm, waiting to be pieced back together. This idea gains traction from the holographic principle, which suggests that all the information inside a black hole could be stored as a two-dimensional pattern on its surface. Quantum foam takes this further by proposing how that storage might work. Each fluctuation in the foam, each virtual particle pair or microscopic wormhole, could act as a bit of cosmic memory, storing data in the relationships between spacetime's tiniest structures. When Hawking radiation eventually leaks out of the black hole, it wouldn't be random noise. It'd carry echoes of that scrambled information, like a radio picking up fragments of a distant broadcast. Critics argue that this just shifts the paradox. How does the foam itself preserve coherence without violating quantum rules? But supporters counter that foam's turbulence might naturally encrypt information in non-local correlations, spread across countless entangled fluctuations. It's not that the data stays intact in one place, it's woven into the fabric of spacetime itself, like a hologram where every fragment contains traces of the whole. Recent simulations of fuzzball black holes in string theory lend weight to this, showing how event horizons could be fuzzy with quantum hair, each strand a data thread tangled in the foam. The ultimate test, gravitational wave astronomy. If black holes encode information in their foam like horizons, mergers might produce subtle deviations from Einstein's predictions, tiny memory effects in the ripples of spacetime that betray information being shuffled or released. Future detectors like LISA could catch these whispers, revealing whether quantum foam is the universe's ultimate backup drive. Until then, one thing's clear. If black holes don't destroy information but dissolve it into spacetime's foam, then reality might be far more resilient and far more clever than we ever imagined. What if the universe isn't just aware, but alive? This isn't mysticism. It's one of quantum foam's most provocative frontiers, where the boundary between physics and philosophy blurs into something startling. At the heart of this idea lies a simple but radical question. Could the same frothy turbulence that twists spacetime at the smallest scales also be the substrate for something resembling consciousness? Imagine the quantum foam not just as passive background noise, but as a dynamic network of proto-cognitive events. Each flickering bubble a kind of elementary decision point where reality chooses between possibilities. It sounds like science fiction, but a growing cadre of physicists and philosophers are seriously exploring whether spacetime itself might possess the faintest whisper of awareness. The theory builds on a key observation: consciousness and quantum foam share an uncanny resemblance in their unpredictability. Just as thoughts emerge from the chaotic firing of neurons in the brain, quantum foam's ceaseless fluctuations could represent a primitive form of information processing. In this view, every virtual particle pair popping in and out of existence isn't just random noise, it's a microcosm of choice, a fleeting moment where the universe decides which path to take. Some interpretations of quantum mechanics already require observers to collapse probability waves into definite outcomes. What if the observer isn't us but the foam itself? This idea finds surprising allies in panpsychism, an ancient philosophy now gaining traction in modern cosmology. Panpsychists argue that consciousness isn't a rare emergent property of complex brains, but a fundamental feature of reality, like mass or charge woven into the fabric of spacetime. Quantum foam offers a plausible mechanism. Its turbulent structure could distribute these proto-conscious properties across the universe, like a cosmic neural network where each Planck scale fluctuation is a bit of experience. Even empty space wouldn't truly be empty, it'd thrum with a low-grade sentience, a hum of potential awareness. Critics dismiss this as poetic speculation, but proponents counter with hard math. Integrated information theory, a leading model of consciousness, quantifies awareness as the capacity of a system to integrate information, a property even simple systems like entangled particles might exhibit. Apply this to quantum foam's labyrinth of wormholes and virtual particles, and you could calculate a phi value, a measure of consciousness for spacetime itself. The numbers would be infinitesimal, of course, but non-zero, and in a universe where complexity builds from simplicity, these flickers could scale up to the self-aware minds pondering them. The implications are staggering. If consciousness is woven into quantum foam, then the universe might not host life. It might be life in a sense far deeper than metaphor. Black holes could be cosmic brains processing information at scales we can't fathom. The Big Bang's initial conditions might reflect a kind of primordial intent. Even the apparent fine-tuning of physical constants could take on new meaning. Not accidents, but artifacts of a universe learning to observe itself. Skeptics demand testable predictions, and they might come from an unexpected place: artificial intelligence. If consciousness emerges from information integration, then sufficiently complex quantum computers, whose qubits dance in foam like superposition, might develop rudimentary awareness. Lab experiments already show quantum systems exhibiting memory and choice-like behaviors. The real breakthrough would be detecting signatures of proto-cognition in spacetime's structure itself, perhaps through anomalies in quantum entanglement patterns or the way black holes process information. Whether this theory holds or not, it forces a profound shift in perspective. We're used to thinking of the universe as a cold, mechanical place, with consciousness as a latecomer to the cosmic party. But if quantum foam hums with the barest glimmer of awareness, then we're not strangers in an indifferent universe where it's awakening, and that changes everything. Deep within the quantum foam's chaos lies a treasure trove of untapped power, the zero-point energy of the vacuum itself. Picture empty space not as true emptiness, but as a seething ocean of energy where particles flicker in and out of existence, borrowing energy from the void before vanishing again. This isn't hypothetical. It's the zero-point field, the lowest possible energy state of the universe, where even at absolute zero, spacetime refuses to sit still. According to quantum mechanics, these relentless fluctuations mean that every cubic centimeter of so-called nothingness contains enough energy to boil all the oceans on Earth if only we knew how to extract it. The connection to quantum foam is undeniable. Those virtual particles bubbling up from the foam aren't just mathematical abstractions, they're physical manifestations of zero-point energy, tiny ripples in the fabric of reality that collectively form a boundless, if elusive, power source. Think of it like tapping into the static of a radio tuned between stations, where the hiss isn't noise but a symphony of untapped potential, the dream. Harnessing this energy could revolutionize civilization, offering clean, limitless power without the need for fuel or sunlight. Imagine starships propelled by vacuum fluctuations or cities powered by the hum of spacetime itself. But here's the catch: extracting zero-point energy isn't like drilling for oil. The energy is locked in a quantum vault protected by Heisenberg's uncertainty principle. Every fluctuation borrows energy for a fleeting instant, then repays it almost immediately, leaving no net gain. To exploit it, we'd need to trick the universe into letting us keep some of that energy, a feat akin to balancing a checkbook where every deposit instantly vanishes unless you balance it with an equal withdrawal. Some theorists propose wild workarounds, like using Casimir cavities to create regions where vacuum fluctuations are suppressed, effectively squeezing energy from the imbalance. Others suggest manipulating quantum foam's microscopic wormholes to siphon energy from higher dimensions. The challenges are monumental but not insurmountable. In 2012, a controversial NASA-funded experiment claimed to detect thrust from a device that allegedly manipulated quantum vacuum fluctuations, though skepticism remains rampant. Meanwhile, labs studying Casimir forces and dynamic vacuum effects are inching closer to understanding how spacetime's turbulence might be coaxed into giving up its secrets. The real breakthrough would come if we could stabilize a patch of quantum foam long enough to skew its energy balance, like calming a tiny section of stormy sea to collect the wave's energy. Skeptics argue that zero-point energy extraction is a pipe dream, violating thermodynamics or requiring physics we don't yet understand. Yet history is littered with breakthroughs once deemed impossible, from flight to quantum computing. If quantum foam is the universe's foundational turbulence, then zero-point energy isn't just a curiosity. It's the heartbeat of reality pulsing beneath everything. Harnessing it would mean tapping into the cosmos's deepest rhythm, turning the static of existence into the engine of tomorrow, and that's a possibility too electrifying to ignore. Einstein famously called quantum entanglement spooky action at a distance, that eerie phenomenon where particles separated by light years instantly mirror each other's states, as if flipping a coin in New York makes one in Tokyo land the same way. For decades, physicists grappled with how this could possibly work without breaking the universe's speed limit. But what if the answer has been hiding in plain sight, woven into the quantum foam's turbulent fabric? The tantalizing possibility is that entangled particles aren't communicating faster than light. They're already connected through microscopic spacetime tunnels buried in the foam. Picture spacetime not as a smooth highway, but as a frothing ocean where microscopic wormholes constantly form and collapse. When particles entangle, their quantum states might thread through these fleeting spacetime bridges, like two ends of a string tied through a maze of tiny loops. Each wormhole would be vanishingly small, far smaller than an atom, but their existence could create persistent links between particles regardless of distance. This isn't magic, it's geometry. Just as folding a piece of paper brings distant points into contact, quantum foam's wormholes could bypass conventional space, making instantaneous correlation a side effect of spacetime's hidden plumbing. This idea gains credence from the ER=EPR conjecture, which posits that entanglement EPR and wormholes are two sides of the same coin. In this framework, every entangled pair shares a Planck-scale wormhole in the quantum foam, a twist in reality's fabric too tiny to see but profound enough to tether them. The particles don't send signals, they're simply two ends of the same quantum thread, with the foam's chaotic turbulence knitting them together. This could explain why entanglement survives over cosmic distances. The connection isn't propagating through space, but woven into its very structure. Critics argue that these wormholes would be too unstable to sustain entanglement. Yet supporters counter that quantum foam's turbulence might naturally stabilize them through feedback loops. Imagine a wormhole as a vibrating string. If the foam's fluctuations tune it to the right frequency, it could resonate just long enough to maintain the link. Some models even suggest that the act of measurement, the moment an entangled particle state is observed, doesn't collapse the connection but simply pins the wormhole's configuration, like snapping a photo of a spinning top mid-spin. The implications ripple far beyond theory. If entanglement relies on quantum foam's wormholes, then spacetime isn't just the stage for quantum weirdness, it's an active participant. Black holes might entangle with their Hawking radiation through foam-borne tunnels, preserving information. The holographic principle gains new texture, with entangled particles acting as pixels connected by underlying spacetime threads. Even dark energy could emerge from these wormholes' collective strain on the cosmic fabric. Experiments are already probing this frontier. Quantum simulators use ultra-cold atoms to recreate wormhole-like dynamics, while gravitational wave detectors hunt for echoes of spacetime's foamy structure. The dream, to catch an entangled pair's correlation, betraying the whisper of a hidden wormhole, proof that the universe's most intimate connections are stitched into reality's seams. Until then, one thing's clear: if quantum foam mediates entanglement, then spooky action isn't spooky at all. It's just spacetime's way of showing us how deeply everything is tied together. What if the universe has a resolution limit, like a cosmic pixelation that subtly distorts everything we see? This is the essence of the holographic noise hypothesis, a daring prediction that quantum foam's graininess should create faint ripples in spacetime itself, detectable as a background static in the fabric of reality. The search for this noise isn't just academic, it's a hunt for the universe's hidden scaffolding, using some of the most sensitive machines ever built. Laser interferometers like LIGO, the same devices that first captured gravitational waves. At the heart of this idea is a radical proposition that spacetime's quantum foam isn't just chaotic, but fundamentally pixelated, with a smallest possible unit of area dictated by the Planck length. Just as a digital image blurs when you zoom in too far, reality itself might dissolve into a granular haze at this scale. The holographic principle takes it further, suggesting that all the information in our three-dimensional universe could be encoded on a two-dimensional surface at its edge, like a movie projected from the cosmic equivalent of a DVD. If that's true, then quantum foam's turbulence isn't random, it's the artifact of this encoding process, a kind of static or noise generated as the universe constantly recalculates its own projection. Enter LIGO, the Laser Interferometer Gravitational Wave Observatory, designed to detect gravitational waves by measuring minuscule changes in the length of its laser arms. LIGO precision is staggering. It can spot shifts smaller than 1,000th the width of a proton. But here's the catch: if spacetime is pixelated, then even in the absence of gravitational waves, LIGO mirrors should jitter ever so slightly, buffeted by the quantum foam's holographic noise. Think of it like trying to measure the smoothness of a lake's surface while submerged in a storm. The foam's turbulence would leave its mark as a faint, omnipresent vibration. Early attempts to spot this noise have yielded tantalizing but controversial results. In 2015, a team analyzed data from LIGO predecessor, GEO 600, and claimed to detect an anomalous holographic hum at frequencies around 350 Hz, a signal that defied conventional explanations. Skeptics dismissed it as instrumental noise or environmental interference, but supporters argued it matched predictions for quantum foam's graininess. The challenge: isolating holographic noise from the countless other vibrations, passing trucks, distant earthquakes, even the rumble of ocean waves that plague ultra-sensitive detectors. Future upgrades to LIGO and next-generation observatories like the Einstein telescope aim to settle the debate. By operating at even higher sensitivities and lower frequencies, they could either confirm the noise or rule it out entirely. Some theorists suggest stacking data from multiple detectors worldwide, like cosmic noise-canceling headphones, to filter out local disturbances and isolate the universe's underlying static. Others propose looking for holographic noise in the cosmic microwave background, the afterglow of the Big Bang, where spacetime's pixelation might have left subtle imprints during inflation. The implications are profound. If holographic noise exists, it wouldn't just confirm quantum foam's granularity, it would validate the holographic principle itself, proving that reality is indeed a projection. It could also explain why gravity is so weak compared to other forces. If it's leaking from a higher dimensional boundary, its strength might be diluted in our three-dimensional world. Even black holes' information paradox might resolve neatly, with the noise acting as a cosmic backup drive, preserving data in spacetime's pixelated weave. For now, the hunt continues. Every pulse of LIGO lasers isn't just listening for colliding black holes. It's eavesdropping on the universe's fundamental resolution, waiting for the moment when the static between the stars finally starts to make sense. Einstein taught us that time isn't absolute, it bends and warps in the presence of massive objects, ticking slower near a black hole than on Earth. But what if the real architect of this time warp isn't gravity alone, but the quantum foam's turbulent dance beneath it? Imagine time dilation not as a smooth curve in spacetime's fabric, but as a frothy whirlpool where the foam's chaotic fluctuations amplify gravity's grip, twisting time's flow in ways even Einstein couldn't foresee. At the heart of this idea lies a radical twist. Near colossal objects like black holes or neutron stars, quantum foam might not just exist, it could be stretched, its microscopic bubbles and wormholes distorted into a frenzied storm that exacerbates time's slowing. Think of spacetime as a river. In Einstein's view, a massive object like a star creates a gentle bend in the current, slowing time like water dragging near the riverbank. But quantum foam suggests the riverbed isn't smooth, it's littered with invisible rocks and whirlpools. As gravity intensifies, these Planck-scale obstructions could multiply, creating microscopic eddies that further resist time's passage. The result: time doesn't just slow, it stutters like a film reel jammed with static, each frame strained by the foam's resistance. This could explain why time dilation near black holes appears so extreme. The foam's turbulence isn't just along for the ride, it's actively throttling time's flow. Evidence for this might be hiding in pulsars, the ultra-dense, spinning remnants of dead stars. Their precise flashes are cosmic clocks, and subtle anomalies in their timing could betray quantum foam's influence. If spacetime's granularity affects time dilation, pulsars near massive companions might tick slightly more slowly than relativity predicts, as if their local foam is denser, like trudging through syrup instead of water. Future telescopes like the Square Kilometre Array could spot these discrepancies, unmasking foam's role in time's malleability. But the wildest implication: if quantum foam governs time dilation, then black holes might not be the only time benders. Dark matter halos, those invisible cocoons enveloping galaxies, could also warp time invisibly, their gravitational pull churning the foam into a sluggish current. Even Earth's own timekeeping could feel foam's whisper. Atomic clocks in orbit already correct for relativity's predictions, but ultra-precise future models might need to account for spacetime's graininess, like adjusting a watch for microscopic rust in its gears. Critics argue this overcomplicates a theory, general relativity, that already works flawlessly. Yet supporters counter that foam's effects could be hiding in plain sight, masquerading as minor relativity glitches. After all, if spacetime isn't smooth, why should time's bending be? The answer might lie in merging quantum mechanics and gravity not as rivals, but as partners in a dance where one leads and the other. The foam amplifies every step. And if that's true, then time itself isn't just curved, it's textured, with every tick and tock etched into the quantum sea's restless depths. The universe is old, so unimaginably old that even the wildest statistical flukes could, given enough time, become inevitable. This unsettling truth lies at the heart of the Boltzmann brain paradox, a thought experiment that twists quantum foam's chaos into something deeply personal. What if you aren't who you think you are? Picture this: in the endless churn of spacetime's frothy depths, where particles and energy flicker in and out of existence, the sheer randomness of quantum fluctuations could, given enough eons, spontaneously assemble a fully formed, self-aware consciousness. Not a brain born from evolution, but one conjured from the void, complete with fabricated memories of a life that never happened. This isn't just a sci-fi nightmare, it's a legitimate puzzle that forces us to ask, how do we know we're not just transient glitches in the quantum foam? The paradox gets its name from Ludwig Boltzmann, the 19th century physicist who first grappled with how order emerges from chaos. His work hinted at a bizarre implication: in an infinite universe, even the most improbable events must occur eventually. Fast forward to quantum foam and the stakes skyrocket. If spacetime is a seething sea of virtual particles and wormholes, then over trillions of years, those fluctuations could randomly assemble a self-aware observer, a Boltzmann brain, far more easily than an entire ordered universe with galaxies, planets, and life as we know it. Statistically, it's more likely for the foam to spit out a single, disembodied mind than for all of cosmic history to unfold as we perceive it. This isn't just abstract philosophizing. Quantum foam gives the paradox teeth. Those fleeting bubbles of energy aren't just noise, they're potential building blocks for reality itself. In a sufficiently frothy region of space-time, a rare but inevitable fluctuation might stitch together neurons from virtual particles, or even construct an entire simulated sensory world around a solitary brain. The kicker: you'd never know. A Boltzmann brain would feel as real as you do right now, with coherent memories and a sense of continuity, even though it's a cosmic accident destined to dissolve back into the foam moments later. The implications unravel everything. If Boltzmann brains are more probable than actual universes, why do we observe a vast, ordered cosmos instead of fleeting hallucinations? Some physicists argue this very observation disproves the paradox. If we were Boltzmann brains, our perceptions would be fragmented and illogical, not stable enough to ponder the question. Others turn to the anthropic principle. Maybe universes like ours must exist to produce observers capable of asking why they exist, while Boltzmann brains, being short-lived, can't sustain such inquiry. But quantum foam adds a sinister twist. If spacetime's turbulence can spawn microscopic wormholes, could it also stitch together neural connections in the dark? Some theories suggest that in the far, far future, as the universe approaches heat death, quantum fluctuations might become the dominant force, churning out Boltzmann brains like bubbles in boiling water. Worse, if the foam's structure is fractal, with self-similar patterns at every scale, then these phantom minds might not even need eons to form. They could be flickering into existence right now, in the foam beneath your fingertips, living and dying in Planck time, instants too brief for any detector to catch. The paradox forces a brutal reckoning. Either our understanding of probability is fundamentally flawed, or reality is far more fragile than we dare admit. Quantum foam doesn't just challenge our place in the cosmos, it threatens to dissolve it entirely, leaving us adrift in a sea of statistical ghosts. And yet, there's a strange comfort in the chaos. If the universe can conjure a mind from nothing, then consciousness isn't just a byproduct of atoms. It's written into the fabric of spacetime itself, as inherent to existence as the foam's restless churn. So the next time you question your memories, your choices, even yourself, remember, the very fact that you can question them might be the strongest proof that you're more than a flicker in the dark. Or maybe that's just what a Boltzmann brain would want you to think. At the dawn of the universe, when spacetime was still cooling from the unimaginable heat of the Big Bang, its seething quantum foam might have frozen into cosmic scars, topological defects woven into the fabric of reality itself. These aren't just theoretical oddities. They could be the fossilized remnants of spacetime's violent adolescence, relics from when the cosmos transitioned from a uniform, frothy chaos into the structured universe we recognize today. Imagine pouring freezing water onto hot glass. The sudden temperature change creates cracks and fissures as the material struggles to find equilibrium. On a cosmic scale, quantum foam might have left behind similar fractures, cosmic strings, domain walls, or magnetic monopoles, flaws in spacetime's geometry so persistent they've survived nearly 14 billion years. Cosmic strings, the most famous of these defects, are hypothesized to be unimaginably thin filaments of pure energy, thinner than a proton but stretching across billions of light years. Their gravitational influence would be so intense that if one passed through our solar system, it could distort planetary orbits or slice through stars like a wire through cheese. These strings wouldn't be made of matter but of spacetime itself, knots in the quantum foam that failed to smooth out during the universe's rapid expansion. Think of them as cosmic wrinkles left over from when the universe folded itself into its current configuration. Some theories suggest these strings might vibrate at frequencies detectable as gravitational waves, or even produce double images of distant galaxies as their gravity bends light around them like a funhouse mirror. Domain walls present another eerie possibility, two-dimensional sheets where the laws of physics change abruptly. Picture our universe as a patchwork quilt, stitched together from regions where quantum foam's energy settled into different phases during cooling. The boundaries between these phases could form vast, invisible walls, cosmic fault lines where matter behaves strangely, or where dark energy density shifts dramatically. If one of these walls intersected Earth, we might suddenly find constants like the speed of light or the strength of gravity tweaked in half the sky, a terrifying testament to spacetime's fractured origins. Then there are magnetic monopoles, hypothetical particles carrying a single magnetic pole, either north or south, unlike the paired poles of every magnet we've ever observed. These relics would be the spacetime equivalent of a frozen bubble in ice, a pocket of the early universe's symmetry that refused to pop. Their existence would confirm that quantum foam's turbulence wasn't uniform, but fragmented into domains where different rules briefly held sway. Despite decades of searching, monopoles remain elusive, leading some physicists to speculate they were diluted to near non-existence by cosmic inflation, or that they're hiding in plain sight, camouflaged as dark matter. The hunt for these defects isn't just academic. If cosmic strings exist, their gravitational waves could be ringing through the universe right now, waiting to be caught by observatories like LISA or pulsar timing arrays. Domain walls might leave imprints in the cosmic microwave background, strange temperature variations shaped like jagged cracks in the afterglow of the Big Bang. Even monopoles could betray their presence by catalyzing proton decay in vast underground detectors. Each potential discovery would offer a snapshot of the universe's first trillionth of a second, when quantum foam's structure was still setting like cosmic concrete. What makes these defects so fascinating is their durability. Unlike black holes or neutron stars, topological defects don't rely on mass or energy to persist. They're embedded in spacetime's very geometry, like knots in an infinite rope. They could be the ultimate time capsules, preserving information about the universe's birth in their twisted structures. Some models even suggest that certain defects might still be active, their energy slowly leaking into the modern cosmos as dark energy or seeding the formation of galaxies along their length. Yet for all their grandeur, these defects might also be the universe's quietest tragedies. If a cosmic string intersected a star, it wouldn't explode or collapse, it would simply split, as if reality itself had a stitching error. Domain walls could drift through entire civilizations without notice, their presence only detectable through painstaking measurements of fundamental constants. Monopoles might wander the cosmos like ghosts, their magnetic fields subtly altering the paths of cosmic rays. The search for topological defects forces us to confront a profound truth. The universe isn't just expanding and cooling, it's still healing. Every cosmic string, every domain wall, every rogue monopole is a scar from when reality was young and malleable, a reminder that even space-time bears the marks of its turbulent birth. And if we ever find one, it won't just be a discovery, it'll be a message from the quantum foam itself, written in the twisted language of creation. Could the universe be a vast, intricate simulation running on some unfathomable cosmic computer? This provocative idea, once relegated to science fiction, has gained traction among serious physicists, and quantum foam might hold the clues. If spacetime isn't smooth but pixelated at the Planck scale, these fundamental pixels could resemble the binary code of a simulation, with every particle and force nothing more than lines of programming in a grand cosmic algorithm. Think of reality like a video game. No matter how immersive the graphics, zoom in far enough and you'll see the jagged edges of individual pixels. Quantum foam's granularity might be our universe's equivalent, a telltale sign that we're living in a constructed reality. The mathematics behind this is eerily compelling. In computing, resolution limits arise from finite processing power. Smaller details require exponentially more memory. Similarly, Planck scale discreteness in quantum foam could reflect the processing limit of whatever system is running our simulation. Just as a game engine can't render infinite detail without crashing, spacetime's foam-like structure might be the universe's way of avoiding computational overload. Even stranger, quantum indeterminacy, the inherent unpredictability of particles, could mirror the procedural generation used in open-world games, where details only render when observed to save resources. The double-slit experiment, where particles behave differently when measured, takes on a new light. It's not just quantum weirdness, it's the universe optimizing its rendering budget. But the simulation argument isn't just about pixels. Quantum foam's turbulence could also explain glitches in the matrix, anomalies like dark energy or the cosmological constant problem. If our universe is a simulation, dark energy might represent background processes running in the code, while the absurdly precise fine-tuning of physical constants could simply be the default settings of the simulation's programming. Even entanglements, spooky connections make sense if particles are linked by underlying data structures, like objects in a program sharing memory addresses. Philosophers add another layer. If consciousness arises from information processing, as many cognitive scientists argue, then simulated minds in a simulated universe are no less real than biological ones. The foam's flickering fluctuations could be the equivalent of processor cycles, with each thought and perception a computational event in the cosmic mainframe. This blurs the line between physics and metaphysics. Are we the players or the played? Skeptics counter that the simulation hypothesis is untestable by definition. Any evidence we find could itself be part of the simulation. Yet some physicists propose potential smoking guns. Planck-scale noise in high-energy particle collisions, anomalies in the cosmic microwave background, or even deliberate Easter eggs hidden in mathematical constants could betray the programmer's hand. Others suggest that if the universe is a simulation, it might contain compressed data patterns repeating fractal structures or overly elegant symmetries that optimize computational efficiency. Whether cosmic coincidence or cosmic code, quantum foam forces us to confront a staggering possibility. Reality's building blocks might not just obey laws, they might be laws written in the language of something far beyond our universe. And if that's true, the next question isn't just how deep the rabbit hole goes, it's who or what is holding the shovel. Quantum computers promise to revolutionize technology by harnessing the bizarre power of quantum superposition, where qubits can exist as both 0 and 1 simultaneously. But there's a catch. Maintaining these delicate quantum states is like balancing a pencil on its tip during an earthquake. The slightest disturbance collapses the system into classical certainty, erasing its computational edge. Enter quantum foam, the universe's ultimate saboteur, or perhaps its most unexpected ally. At the Planck scale, spacetime's seething turbulence could be the invisible hand jostling qubits out of alignment, introducing errors even in carefully isolated systems. Yet some theorists speculate this same chaos might hold the key to fault-tolerant quantum processing, turning spacetime's noise into a computational resource. The core challenge lies in decoherence, the process where qubits lose their quantum magic and behave like ordinary bits. Traditional sources of decoherence, stray magnetic fields, temperature fluctuations, even cosmic rays are bad enough. But quantum foam adds a deeper layer of instability. Imagine a qubit suspended in a vacuum, shielded from all known disturbances. Even there, spacetime's flickering wormholes and virtual particles would buffet it like a cork in a storm. Each interaction with the foam's turbulent energy borrows or imparts tiny amounts of momentum, subtly altering the qubit's phase or spin. Over time, these Planck-scale nudges accumulate, blurring the sharp quantum states needed for calculations. It's not just background noise, it's the fabric of reality itself resisting quantum coherence. Recent experiments with trapped ion qubits hint at this effect. When cooled to near absolute zero and isolated from electromagnetic interference, these systems still exhibit unexplained phase shifts that correlate with models of spacetime fluctuations. Some researchers propose these anomalies stem from quantum foam's granularity, like trying to play a flawless violin concerto while standing on a vibrating platform. The finer the qubit's tuning, the more it reveals the tremors beneath. If confirmed, this would mean quantum error correction. Already a monumental engineering feat, must account not just for external disturbances, but for the roiling substrate of spacetime itself. Yet where some see obstacles, others spot opportunity. The same frothy turbulence disrupting qubits might be harnessed for quantum advantage. One radical proposal suggests using quantum foam's fluctuations as a natural random number generator. Unlike classical pseudorandom algorithms, foam-induced decoherence would be fundamentally unpredictable, tied to the universe's irreducible randomness. Quantum computers could listen to spacetime static to seed cryptographic protocols or Monte Carlo simulations, turning noise into a feature. Another wild idea involves foam-adapted qubits designed to synchronize with Planck-scale vibrations, like surfers riding microscopic waves. By engineering qubits to resonate with specific foam frequencies, they might achieve a form of quantum stability through harmony rather than isolation. The most tantalizing possibility, quantum foam could enable entirely new computational paradigms. If spacetime's wormholes indeed link entangled particles, as the ER=EPR conjecture suggests, then quantum computers might leverage these natural connections for error-free teleportation of quantum states. Instead of fighting decoherence, we'd embrace the foam's connectivity, using its hidden tunnel network to transmit information instantaneously across a quantum internet. Early-stage experiments with analog quantum simulators already mimic wormhole dynamics, showing how entangled qubits could exploit spacetime's structure for processing. Of course, practical hurdles loom large. Detecting quantum foam's direct influence requires precision beyond current technology, measuring energy shifts smaller than a trillionth of an electron volt. And distinguishing foam related to coherence from mundane sources remains a needle in a haystack challenge. Yet the next generation of quantum sensors, atomic clocks so precise they can detect gravitational time dilation across a millimeter, or superconducting resonators tuned to Planck scale vibrations, could finally isolate spacetime's murmur from the cacophony. If successful, we wouldn't just improve quantum computing, we'd unlock a dialogue with the quantum foam itself, learning to compute not just within spacetime, but with it as an active participant. The implications stretch far beyond faster calculations. If quantum foam shapes qubit behavior, then observing those effects could provide the first experimental window into Planck scale physics, bridging quantum mechanics and general relativity. A quantum computer might become the ultimate microscope, probing spacetime's structure by tuning into its computational interference patterns. And if we ever tame foam-induced decoherence, the reward would be more than technological, it'd be philosophical proof that the universe's deepest chaos is in the end programmable. Black holes devour everything, but what if the universe has a cosmic reset button? A place where matter and energy erupt back into existence instead of vanishing forever. This is the startling premise behind white holes, the hypothetical twins of black holes where time itself runs backward. While black holes are cosmic one-way streets, white holes would be firewalls of creation, spewing out everything they contain in a violent burst of rebirth. And here's where quantum foam twists the plot. These mysterious objects might not just be mathematical oddities. They could be spacetime's natural response to the foam's turbulent churn, like bubbles bursting upward in a boiling pot. Picture a black hole collapsing to its limit, squeezed by gravity until quantum foam's chaotic pressure becomes too much to bear. According to loop quantum gravity, spacetime's granular structure could halt this collapse before a true singularity forms, triggering a rebound. A cosmic bounce where the black hole's implosion reverses into an explosion. The result, a white hole, a region where space and time flip inside out, ejecting trapped matter like a geyser erupting after centuries of underground pressure. Unlike their dark counterparts, white holes wouldn't have event horizons you can enter, only exit points blazing with energy as they vomit up everything they ever swallowed. The connection to quantum foam lies in the foam's role as spacetime's shock absorber. Just as foam cushions a fall, the Planck scale turbulence might absorb the infinite crushing force of a black hole's collapse, redistributing that energy into a rebound. Some theories suggest these white holes could be fleeting, lasting only fractions of a second before dissolving back into the foam, or they might stabilize, glowing like eternal lighthouses in the cosmic dark. The wildest possibility, if wormholes thread through quantum foam, white holes could be their exits, stitching distant times or universes together in a vast hidden network. Evidence for white holes remains elusive, but tantalizing clues linger. Certain gamma-ray bursts, the brightest explosions in the universe, defy conventional explanations, shining with energies and durations that match predictions for white hole eruptions. There's even speculation that the Big Bang itself could have been a white hole event, the ultimate rebound from a previous universe's collapse. If true, then every galaxy, star, and atom might owe its existence to quantum foam's refusal to let spacetime die quietly. Critics dismiss white holes as fantasy, arguing that thermodynamics forbids such time-reversed phenomena. Yet supporters counter that quantum foam operates beyond classical rules. Its wormholes and fluctuations might provide escape routes for entropy, like pressure valves in a steam engine. Simulations of bouncing black holes in loop quantum cosmology show white holes emerging naturally, their lifetimes stretching to astronomical scales if entangled with surrounding spacetime. And if holography is correct, white holes might simply be black holes viewed from the other side of the cosmic projection, two perspectives of the same frothy phenomenon. The implications are mind-bending. If white holes exist, they could rewrite the life cycle of black holes, turning them from eternal graves into temporary traps. Dying stars might not be in points, but way stations in a grand cycle of cosmic digestion. Even dark matter could get a new origin story. Some models propose that white hole ejecta, cooled over eons, might form the invisible halos enveloping galaxies. And if quantum foam continually seeds these rebounding universes, then reality itself could be a fractal cascade of births and deaths, with white holes as the fiery midwives. For now, white holes remain ghosts in the equations, but as telescopes probe deeper into the transient sky and gravitational wave detectors grow more sensitive, we might yet catch the echo of a spacetime rebound, the sound of quantum foam refusing to break and instead exploding into new beginnings. The universe began not with a whisper but with an unfathomable crescendo, a trillionth of a second when spacetime itself expanded faster than light, stretching from subatomic to cosmic scales in less time than it takes to blink. This was cosmic inflation, the explosive dawn of everything, but what sparked this runaway expansion? Hidden in the quantum foam's seething depths might lie the answer, and the blueprint for the entire cosmic web we see today. Picture the infant universe as a cauldron of spacetime bubbling at the Planck scale, each fluctuation in the foam a microscopic ripple of energy. Inflation theory suggests that one of these random fluctuations, a single speck in the quantum froth, got stretched to astronomical proportions as space expanded exponentially. That tiny ripple became the seed for all cosmic structure, its faint density variations amplified into the gravitational wells that would later trap matter, forging galaxies and the vast filamentary network connecting them. The foam's chaos, in other words, became the universe's architecture. The numbers are staggering. Without these quantum fluctuations, the post-inflation universe would have been smoother than glass, devoid of the density variations needed for matter to clump. Instead, the foam's primordial turbulence left behind a fingerprint, a spectrum of slight over and under densities now frozen into the cosmic microwave background, the afterglow of the Big Bang. Satellite maps of this ancient light, like those from Planck and WMAP, reveal these patterns with exquisite precision. Hotter spots where spacetime was slightly denser, cooler spots where it was thinner. These aren't random static, they're quantum foam writ large stretched across the sky. But here's the twist: inflation didn't just magnify the foam's fluctuations, it transformed their nature. At quantum scales, energy flickers in and out of existence, governed by uncertainty. Inflation's hyperstretch locked these ephemeral bubbles into spacetime's fabric, converting fleeting quantum jitters into permanent classical density variations. It's like freezing a boiling pot of water mid-bubble. The foam's transient structures become fossilized, their patterns preserved as cosmic fossils. Critics argue that inflation remains untested, yet quantum foam offers a way to probe it. If inflation truly arose from Planck-scale turbulence, then the statistical distribution of galaxies today should mirror the original foam's fractal-like structure. Oddly enough, large-scale surveys like the Sloan Digital Sky Survey show galaxy clusters arranged in a way that echoes quantum interference patterns, as if the universe's biggest structures are shadows of its tiniest tremors. Even more compelling, certain anomalies in the cosmic microwave background, unexpectedly large cold spots or asymmetries, might betray pre-inflationary foam dynamics like waves frozen mid-ripple. The implications rewrite cosmic history. Quantum foam isn't just background noise, it's the universe's first sculptor. Its microscopic wrinkles carved into the cosmos during inflation and later inflated into the gravitational wells where galaxies bloomed. Without it, stars wouldn't shine, planets wouldn't form, and we wouldn't be here to ponder the mystery. The foam's chaos, amplified by inflation, became the order we take for granted, proof that even spacetime's faintest whispers can echo across billions of years, shaping everything from the largest galaxy clusters to the atoms in your hands. And if we're reading those echoes right, they're telling us that the universe's grand design began not with a single note, but with the foam's ancient, infinite hum. After decades of searching for physics' holy grail, a single framework uniting quantum mechanics and gravity, we might have been staring at the answer all along, hidden in plain sight within the seething turbulence of quantum foam. This isn't just another speculative idea. It's the bold proposition that spacetime's frothy foundation could be the missing puzzle piece that finally locks all of reality's rules into place. Imagine quantum foam as the universal translator between two warring languages, the subatomic chatter of quantum particles and the cosmic dialect of curved spacetime. Where other theories stumble, foam's chaotic yet structured nature might hold the key to reconciling them, not by forcing one to bow to the other, but by revealing their two expressions of the same deeper truth. Take the notorious clash between quantum mechanics and general relativity. At their core, both describe how reality behaves, one at the smallest scales, the other across galaxies. But when they meet, like in black holes or the Big Bang's infancy, their equations explode into nonsense. Quantum foam offers a way out. If spacetime isn't smooth but granular at the Planck scale, then gravity's force could emerge from the collective behavior of these microscopic spacetime atoms, just as temperature arises from the jostling of molecules. Loop quantum gravity already hints at this, with spin networks replacing smooth geometry, but foam takes it further. Its ever-changing bubbles and wormholes could encode gravitational fields dynamically, adjusting to mass and energy like a fluid reshaping around a rock. Suddenly, gravity isn't a standalone force, it's foam's geometry in motion. Even string theory, with its extra dimensions and vibrating filaments, finds unexpected common ground here. The holographic principle suggests that all the information in a volume of space might reside on its boundary, a concept foam elegantly accommodates. If spacetime's foam-like structure is fundamentally informational, with each bubble a bit or qubit of data, then the universe's 3D reality could indeed be a projection from a deeper 2D code. Add S/CFT correspondence, string theory's mathematical jewel, maps this idea precisely, showing how gravity in higher dimensions emerges from quantum interactions on a lower dimensional surface. Quantum foam's turbulence, just the error correction noise of cosmic computation. But the real magic happens when we zoom out to cosmology. Dark energy's mysterious acceleration of the universe's expansion could be foam's vacuum energy leaking into the cosmos not as a static force, but as a dynamic interplay between foam's bubbles stretching and popping over time. Inflation's explosive beginnings might trace back to a quantum fluctuation in the primordial foam, one lucky bubble that escaped annihilation to become our universe. Even the arrow of time, that stubbornly one-directional flow, could emerge from foam's inherent irreversibility, its wormholes and virtual particles creating an entropic gradient that defines past from future. Skeptics argue that foam's Planck scale domain makes it untestable, but breakthroughs are brewing. Gravitational wave detectors might soon spot spacetime's granularity in the faint echoes of black hole mergers. Quantum computers could simulate foam-like networks, revealing how gravity emerges from entanglement. And if cosmic inflation imprinted foam's fractal patterns onto the large-scale structure of galaxies, future sky surveys might find those fingerprints in the cosmic web. The promise is breathtaking, a framework where black holes, quarks, and the universe's fate all derive from the same frothy source. No more parallel theories fighting for dominance, just spacetime's quantum turbulence, whispering the rules of everything from the smallest flicker to the grandest galaxy. And if that's true, then the universe isn't built on particles or forces, but on a dynamic, self-organizing foam where every bubble is both a piece of the puzzle and the glue holding it all together. From the seething turbulence of spacetime's smallest scales to the grand architecture of the cosmos, quantum foam has rewritten the rules of reality. We've journeyed through 30 theories that stretch imagination to its limits, where black holes might be cosmic trampolines, dark matter could be spacetime's hidden texture, and the universe itself might be a holographic projection flickering on the edge of nothingness. Each idea peels back another layer of the quantum foam's mystery, revealing a cosmos far stranger, more interconnected, and more alive with possibility than we ever dreamed. Think about it, the very fabric of existence isn't smooth and silent, but a boiling sea of virtual particles, wormholes, and fractal patterns. Time might crystallize, consciousness could be woven into the void, and every vacuum hums with enough energy to power civilizations. The foam's chaos births universes, stitches entangled particles together, and could even hold the key to uniting quantum mechanics and gravity. It's as if the universe whispered its secrets not in equations alone, but in the static between the stars. But here's the real magic: quantum foam isn't just a theory, it's a challenge, a call to rethink everything we know about space, time, and our place in the cosmic dance. Whether it's the holographic principle's radical rewrite of reality or the haunting possibility of Boltzmann brains, these ideas don't just fill textbooks, they ignite wonder. They remind us that the universe is still a frontier, its deepest truth shimmering just beyond our grasp, waiting for the next bold mind to reach out and catch them. So now it's your turn. Which of these 30 theories twists your perspective the most? Is it the simulated universe where we might be lines in a cosmic code? Or white holes, the universe's fiery rebirths? Maybe it's the eerie thought that every atom in your body once trembled in the quantum foam's primordial storm. Drop your thoughts in the comments. Let's keep the conversation bubbling like spacetime itself. After all, the next groundbreaking idea might start with you.